For this example, we'd like to find a power series representation of the function f of x equals log of 5 minus x. And to do this, we need to maybe think outside the box a little bit. So what we can do is we can start with a function that we know a little bit more about. So first of all, let me just say this. So the derivative, f prime of x for this function, the derivative of this function is, as we know, negative 1 over 5 minus x. Okay, so there's the derivative of f of x. And now we can try to represent this function as a geometric series. This looks like the sum of a geometric series. So let's see what we can do with this. We can take this minus sign from upstairs. Actually, we don't want to. We want to leave it there because what we're trying to do, we want to make sure that this series looks like a naught over 1 minus r, right? Where the r is usually in terms of the x. So what we can do, what we really have to do here is just factor out this 5 from the bottom, right? And so we've got our negative 1 upstairs. We end up with 1 minus, but then it's x over 5 down here. Okay, and we rewrite this then as negative 1/5 all divided by 1 minus x over 5. And when we look at this, this looks exactly like this, right? So the negative 1/5 becomes the a naught, the x over 5 becomes the r, and we know how to write this series down then. So this is as a power series, this is the sum, and goes from 0 to infinity, a naught r to the n. So again, based on this just observation, comparison with a general geometric series, we then have that this is negative 1/5 times x over 5 to the power n, and this can be written then as, again, sum n equals 0 to infinity, negative 1 over, this one becomes 5 to the n plus 1, because you have 5 to the n and another one, right? All times x to the n. So this is a power series. By the way, this power series converges on what interval? So this converges for r less than 1, absolute value of r less than 1. Our r, in this case, is x over 5. And so this means that this converges on the interval where x is between negative 5 and 5. So there's the interval of convergence of the power series that we just found. Now, I've just dived right into this, right? Because I found that the derivative of this function looks like the sum of a geometric series. But if I took the derivative of this function to find the power series, then I didn't find the power series of the function, right? So what I need to do next is I need to undo the derivative, right? So we have just found that f prime of x is equal to sum n goes from 0 to infinity, negative 1, 5 to the n plus 1, x to the n, right? And I want to undo this derivative. So how do you undo a derivative? Well, you integrate, right? So integrate both sides with respect to x. We know from the notes that we can integrate this term by term as long as we add our unknown constant. All right, and what we end up with then is our function f of x, which, by the way, we know is the log of 5 minus x, right? The log of 5 minus x is then given by this power series. N goes from 0 to infinity. I'm going to move the unknown constant to the left so that it doesn't look like it's in the sum. So unknown constant plus the power series of the antiderivatives here, right? So we have our negative 1 over 5 to the power n plus 1. Then we have to take the antiderivative of this x term, and so this term is x to the power n plus 1 divided by that power, n plus 1, right? All right, so this is our power series. And at this point, what we should do, we have to figure out what this c is. We can't just leave this, right? We have to figure out what c is. So and so the easiest way to do that is to remember that this power series representation is true at least on this interval, but particularly at the center point, so at x not equal to 0. And what we can do is plug into our power series then, and we can write f of 0, right, is equal to log of 5 minus 0, which is just ln of 5, which equals c plus the sum, n goes from 0 to infinity, negative 1 over 5 to the n plus 1 times n plus 1, all times 0 to the n plus 1. Well, what happens with this term? This term is 0, right? just add up a bunch of zeros, you get 0. And so what we learn then is that the constant, the unknown constant in our integral is not really unknown at all, because our integral is giving us a known function, right? It's giving us back a known function. So our power series then for f of x is equal to, or again, let's write down what our f of x is. The log of 5 minus x. This is equal to the value of the log of 5, natural log of 5, plus the rest of the power series, which starts at n equals 0 to infinity, negative 1 over n plus 1 times 5 to the n plus 1, x to the n plus 1. And at this point, you might see that these powers, all of these n plus 1s show up as n plus 1s, right? And so we could make a shift here, and we can change this so that this starts at n equals 1, and our power series then might look like ln of 5 minus x equals log of 5 plus the sum, n goes from 1 to infinity, negative 1 over n times 5 to the n, x to the n. Okay? And so there's our power series, and this converges, by the way. We need to check the interval of convergence, okay? But this converges on at least the interval, the same interval that we got it from. So it converges on at least the interval where x is between negative 5 and 5. Okay, and we need to check and see, does it converge at the endpoints or not? So we need to check the two endpoints. Now, just as a note here, when you take a derivative, you can never improve the interval, okay? You cannot add the endpoints, but we actually took an integral to build this series, right? We started with a geometric series, and we integrated it. Right here at this step, we integrated it. When you integrate, you can potentially make things nicer. So you can include endpoints that may not have been there before. So we need to check them, in other words, right? So on one hand, log of 5, we know 5 can't be part of the answer, right? Because log of 5 minus 5 over here does not exist. So on one hand, when x equals 5, ln of 5 minus 5, which is ln of 0, right? This is undefined. And if the function itself is undefined, then the power series is not equal to the function, right? So we don't need to do anything else with that one. We'll put a little x there. That one's not in the domain. But what we do need to check is when x equals negative 5. Okay, because log of 10 does make sense. So log of 5 minus negative 5, this does make sense. This is log of 10. All right, and so what we want to know is really, we're not concerned with like comparing with this number. What we want to know though is does this series converge when x is equal to a negative 5? So let's find out. So if we plug in here a negative 5, we have negative 1 over n times 5 to the n times negative 5 to the n, right? We've plugged in negative 5 for x. Goes in here. And then we just compare. So this is now the sum. And from 1 to infinity, this is now going to be negative 1 to the n plus 1. We've got negative 1 to the n and another one here, times 5 to the n upstairs, times n 5 to the n downstairs, right? These two cancel. And look what we're left with. We get at least a portion of our alternating harmonic series. The harmonic series itself we know is divergent, but the alternating harmonic series is convergent. Okay, so when x equals negative 5, this series converges, and what we learn then is that our interval of convergence is the interval, the half-open interval, from negative 5, open, can't be there because of the function itself, to positive 5, closed, converges. Okay, and the reason it converges there is because of the integral.